Alright, we're going to go through some of the technical details of fiber. We had just left off on how fiber is made, so we're going to dig into some of the technical details. Some of this is review of things we said before, but some of it's going to be new. The two phenomena that allow transmission of light through a fiber is your refraction and your reflection. And those were some of the early demos I did for you, showing you the light bending going through the tank of water. That's your refraction. The reflection is like bouncing off of a mirror, if you will. Those are the principles that keep the light in the core of the fiber. The core is super clear glass. The cladding around it is a slightly different index of refraction. That way it will bend the light back into the core, or if it's a larger difference in index of refraction, it will reflect the light back into the core. So these are the phenomena that keep the light in the core of the fiber. I like to think of it this way. Think of a garden hose. The core is the hole in the garden hose, the opening. The cladding is going to be the hose itself. So as I put water into the hose, it's going down through, and the tube, the hose itself, is keeping the water in the core. The cladding is keeping the light in the core. That is the function, and that cladding is there to reflect or refract the light back into the core. Reflect is going to bounce it back in. Refract is going to bend it back into the core of the fiber. And here's just that idea. Your graded index fiber, 5125, is going to refract. It's going to bend the light back into the core. Meanwhile, your step index, 62.5, is going to reflect, bounce the light back into the core. That's your differences, your sizes. And the index of refraction is just that mathematical number to indicate the difference of, I should say, as the light travels through a substance, how much is it going to bend? There is actually a ratio of this, and they measure it to compare it to the speed of light in a vacuum, and then that material itself, glass, plastic, whatever, is going to bend the light some value more than light going through a vacuum. That's your indices of refraction. With our fiber optic, the core and cladding relationship, the core is there to keep the, kind of house the light or hold the light. The cladding is there to bounce it back in. That's why some people think of these as light pipes. Yeah, that's actually a good, good analogy. Or as I said, the garden hose with the water moving through. It's that kind of analogy. Well, how do we send a signal on fiber? Well, the data is modulated. Well, the data coming from my computer, if you will, ones and zeros, are electrical pulses. Well, those electrical pulses go into a converter that's going to convert it into a light pulse. Well, think of it almost like a laser pointer. You have a battery in there generating electrical pulses. It goes to some kind of light, and the light ends up emitting the pulses of light. So I start sending electrical pulses, pulse, no pulse, pulse, no pulse. Well, those electrical pulses go into a light, and the light starts blinking. Flash of light, no flash of light. Flash of light, no flash of light. That is the sending unit. So the beam itself then is focused at the core of the fiber. That's the tough part. Trying to hit a bullseye on a human hair. The light of the light source is aimed at the core of the fiber and is launched into the fiber. At the other end of the fiber, you have some kind of light-sensitive device to detect that light and turn it back into electricity. Well, think of this. If you have a light outside your house that turns on at dark, there's a little photo sensor in there, light sensor in there, a photocell, cadmium sulfide cell. That is there to detect, in this case, the absence of light, and it turns something on. In this case, it turns on an actual light bulb. If you've ever, I laugh because when I was a kid, my neighbor used to yell at me. I would put my thumb over their light outside and turn the light bulb on and off by playing with that little photocell. I just thought that was pretty cool when I was a kid. They'd say, "Stop playing with the light." Okay. Well, there's an example of a receiver, a light-sensitive device on the other end of the fiber. All I need is something like that cadmium sulfide cell, obviously better quality, but a cadmium sulfide cell to detect light and no light, and it would turn it right back into an electrical pulse. That's all it is. A light bulb on one end, and on the other end, a photocell, a cadmium sulfide cell on the other end, to turn that light back into electricity. That's all that's really going on with fiber optic. So they now use the terms of a source and a detector. The source is your light, your laser LED on the sending end of the fiber, and the detector on the other end, the cadmium sulfide cell, is the receiver on the other end, the detector on the other end. Photodiodes and phototransistors are really what they are. They're a lot more sensitive than the cadmium sulfide cell. So the circuitry on the sending end is called the transmitter, and the circuitry on the other end is the receiving end, is the receiver. So here it is, your electrical pulse in. I have my LED or laser light taking an electrical pulse and sending pulses of light down the fiber. On the other end, I have the light coming in, little cadmium sulfide cell, and emitting electrical pulses out. That's all we're doing. That's all it is. So I used to have, pulse of electricity followed by none, pulse of electricity followed by none. Now I have a pulse of light followed by no light, pulse of light followed by no light. That's it. There's really no difference. And there's your transmitter, source, receiver, detector, if you will. That's why most fiber optic connections are simplex. The actual fiber itself, one fiber can transmit data in one direction. So I typically need 2 cables for a complete fiber connection, one for transmitting and one for receiving. That's why our fiber cables that we deal with are typically two fibers here, one for sending, one for receiving. My laser light source is already focused, collimated into a beam. Even your generic little $3 laser pointer is focused into a beam. That does not need much lenses to get it focused into a beam and into the center of a fiber. It doesn't need much of that. Meanwhile, my LED light source, think of LEDs on monitors or computers to say that something's on. That little light is typically an LED saying that thing is on. The laser light source, the LED light source actually does need some focusing into a beam. That's the collimating. And here's trying to show you that idea of whatever my light source is, I typically need to go through a lens to focus it into a beam so it can hit a bullseye on my fiber. That's an important step. Here's a quick comparison of your LEDs and your lasers, just showing the bandwidth, wavelength of these different light sources. And your LEDs are typically multimode fiber, shorter ranges, relatively inexpensive. Your lasers are for typically single mode, very narrow very focused light beam, usually for single mode, longer distances, and costs are much higher, significantly higher for that laser light source. So there's LEDs, lasers. Let's look at LEDs real quick. Your LEDs, there's 2 main types. They're surface emitting and edge emitting. Most of the ones we're used to seeing are surface emitting. These are little bulbs on my monitor or my computer saying it's on. Those are inexpensive and really cheap, and they're very commonly found. The ones I'm typically going to find for fiber optic are edge-emitting diodes. Those actually produce a little bit more focused beam. Here's your surface emitting, like we're used to seeing something's on. Meanwhile, over here is an edge-emitting. The structure of it is a lot different. It's emitting from the edge instead of the surface up here. It's emitting from the edge, so it's kind of a focused beam already. Meanwhile, your laser light sources are typically laser diodes. These are very small and actually produce a very focused beam of light from the get-go. And this is kind of a close-up of a laser diode, and this shows you roughly the size of the thing. There's a penny, and there's the laser diode. The next picture, we're going to pull this lens off right here. I pull that lens off. There it is. I'm going to pull that lens off. Down in there is the emitter surface of the edge-emitting laser diode. Small stuff, yes. Well, I have to have a very small focus beam to be able to hit a bullseye on a human hair, because that's the size of your fiber optic. The book then talks a little bit about VCSELs, vertical cavity service emitter laser. This is a popular laser light source, high bandwidth, low cost, ideal for gigabit and so forth. With this one, here's your VCSEL. Again, you're seeing the very similar look to the thing. Focus beam, okay. With multimode fiber, small defects in the fiber only cause minor attenuation issues. When I'm using a laser light source, though, as that laser light source, that focus beam hits that defect in the multimode fiber, it could literally ricochet off. Almost imagine a super ball hitting something. It's going to bounce off and ricochet off. That's bad news. That's a lot of attenuation. So I need better fiber. They actually make gigabit ready or laser compatible fiber that can handle this, or I need to use the conditional launch adapter. The conditional launch adapter actually takes the laser light source and defocuses it and makes it spread out. Instead of a focused beam, it's going to spread out more to like a multimode light source. But most people have moved on to using the gigabit or laser tune fiber, if you will, for lack of a better term. 568C standard allows for both single mode and multi-mode to be used. Typically we found multi-mode between our closets, single mode maybe between buildings kind of thing. But our standard allows for use of both of these depending on what our need is in our building. We still have been able to keep using multi-mode fiber because in our building we've kept our horizontal cable runs at 90 meters, and multi-mode fiber can usually go 100 to 500 depending on our light source. So that's usually enough to connect closets in our building. So it still has a good use for use in most LAN environments. Typical fiber optic cable configurations. A lot of the stuff we deal with is 2 fiber zip cords, send and receive. But I do also have some other outside plant stuff. We'll show you that in a minute. And I have the tight buffer, loose buffer that we talked about before. There's your zip cord. This is typically what we find for patch cords and connections between closets. But they also do have multi-strand fibers and breakout fibers, depending on the connections that you need to use. Here's where I also remind you of your insulation types, general, riser, plenum. We mentioned this before, so I'm just kind of recapping your memory here, or refreshing your memory. As I look at the label on the outside of a fiber, if I see an OFNG, G is indicating general purpose. This would be plain old polyvinyl chloride insulation, acceptable for user, patch cords, equipment closets, that sort of thing. There's your OFNG. If I see OFNR, riser rated, this is typically used between floors in my building. Wiring closet on this floor to right above me, right directly above me, the closet above me, to connect upstairs. That would be a riser rated cable connecting our 2 floors. OFNR, if you will. And then, last but not least, if I have to install my fiber in a plenum space, I need plenum rated fiber. So therefore, I'm going to be looking for OFNP. P for plenum. This would be plenum rated cable for installing it into a plenum space, perhaps above the ceiling, connecting closets down the hall. So don't forget about those guys that we had mentioned before, just since we're talking fiber and fiber construction. Don't forget, we mentioned the color coding. Typically orange insulation or jacket is multi-mode. Aqua is typically laser optimized 10 gig multi-mode fiber, and yellow is typically single mode. That's not carved in stone, but that's typically the color coding that gets used. Don't forget also on the side of the fiber, all of our labeling that we have, that we've looked at before back in Chapter 5. And again, there's your 2-strand fiber, transmit, receive. And now we're into our connectors. So let's just recap these. We had mentioned these before. We'll recap them again. The common ones you run into over the years: ST, SC, MTRJ, LC. Early fiber connections used ST. These look like little mini BNC connectors. These guys right here. They twist lock connected onto an interface. Had good fiber alignment. This right here has 1 fiber in, so it's good fiber alignment. Things kind of progressed on to using SC. A lot of things used SC ports or SC terminations. This guy right here, kind of a squarish connection with your fiber coming out, the ferrule coming out. Things that moved on to using small form factor. MTRJ was very common for a while. Even some of the switches we have in our room still have MTRJ ports on. This was kind of popular because both fibers were in 1 connector. There's 2 little dots down there, 2 little dots down here are both fibers, send and receive. So in the space of 1 SC connector that we had here, we have our 2 fiber connections. So a lot smaller footprint on my switch or my outlet jack, and I can have both fibers in. But a little bit tougher for fiber alignment. The one that's very popular today and very common today is your LC connector. This one kind of looks like 2 mini SCs. Here's one here, here's one here, and this clip kind of holds them together. So they are terminated individually, and then the clip itself kind of holds them together as a pair. And again, this is about the size of 1 SC connector. This is typically what you find for switch ports. If I'm going to connect 2 switches together, I'm typically going to find an LC connection. And I'm also going to find a lot of my small form pluggable modules. The slide in the switches will be LC connector. So those would be the ones that you typically run into. Multimode are typically going to be beige connectors, and my single mode are typically going to be blue. All right, we'll come back in the next one, continue on with some of our technical specs.